Hi, this is Dale from Newton's Closet, and one of the things that is really confusing for most people is when we're trying to use compass notation and compass vectors, and we have been taught how to do Cartesian coordinate vectors. And so what we're going to do today is we're going to work on how to get the two connected. All right, so if we have a vector A, and say we just have this vector here, and it's 124 miles per hour at 60 degrees. Now that 60 degrees is actually classified as a compass vector. And so because the compass starts at 0 in the north and comes down like this, that 60 degrees sits here. So that's the compass vector. Now, the other vector that we get is the complementary angle, and that comes from here. So that 30 degrees is actually a Cartesian vector. And because that's a Cartesian vector, we can build our triangle, our standard triangle in the Cartesian coordinate world, and we now have the horizontal and vertical values. The horizontal value is 124 cosine 30 because cosine is attached to the horizontal, and we get 107.4. The vertical, 124 times the sine of 30, because it's opposite over hypotenuse. And so that becomes 62 miles per hour. And so we now have the opportunity to get another vector. So if we're adding two vectors within the compass world, we start here with compass being 0, and we come 135. We go past 90 and down here to 40, down here where it's 45 degrees below the x-axis. And in the Cartesian world, that's negative 45. This being 0, that being negative 45. Compass world starts at 0, goes to 90, and then 90 down to 135. And so now we make our Cartesian rectangle, not rectangle, but triangle. And we get bx equals 30 cosine negative 45, and by is 30 sine negative 45. And so you get these two values from these two vectors, and we're going to then try to find the resultant. But what we're going to do is we have two methods. The first method is we're going to use the parallelogram method in order to get this done. Now, if we added these up directly, we get 128.6 and 40.4. But if we do the parallelogram method, we're going to get this value here, because this we draw up here and we draw that in parallel here. As you can see, we have this beautiful parallelogram, and we get this value here, which we call the resultant. Now, this resultant is a combination of these two values, Rx and Ry. All right. And so how do we calculate the actual value of the resultant? It's Rx squared plus Ry squared equals R squared. So it's a Pythagorean theorem application. Then we get the value of 134.92. Then what happens is we take the tangent, and the tangent is Ry over Rx. So 40.8 divided by 128.6, and you get a value of 0.3173. You take the inverse tangent, you get 17.6 degrees. So if we were to draw this resultant, right, and we were to say the resultant is 134.92 miles per hour, our degree is 17.6. It's actually a Cartesian coordinate value. So how in the world do we get that back to the compass value? Well, it's 17.6 from the x-axis right here. And so if we just find the complementary angle for this area right here, that will actually be the compass vector. So we take 90, we subtract 17.6, and we get 72.4. And that value 72.4 is actually the compass vector of the resultant of these two values. Now, if we take a look at what happens in each quadrant, in the first quadrant, if we want to know what the value is, we take 90 degrees and we subtract the value that we have from the x-axis, and that gives us the compass vector. In the fourth quadrant, we take 90 degrees and we add the angle that we get from our Cartesian value. Then what happens in the third quadrant? The third quadrant, we take 270 and we subtract this value, and that'll give us the value from north all the way around to this red vector. And then in the second quadrant, we go 270 and we add that value. So Cartesian vectors and compass vectors are related, and we just need to figure out which quadrant we're in. We still use the Cartesian vector analysis of the constituent vectors ax, ay, bx, and by. We still use our parallelogram in order to figure out where the resultant is. Then we use Pythagoras, the inverse tangent. Then we have to convert it back to the original compass vectors. This is Dale from Newton's Closet. I hope this has been helpful.